Okay, so we're going to pick up here kind of where we left off last week. So we were talking about chapter 2, getting towards the end of it. So last time we talked about the idea of sort of moving away from Bohr's model of orbits, where we're sort of for sure where the electrons are traveling, and this sort of planetary model, moving away to more quantum mechanical model of where we find electrons, which are these orbitals, which are really sort of theoretical prediction sort of maps, probability sort of maps. And there's different types of orbitals, which are really atomic orbitals. And we have S's, we have P's, D's, and F's. There's only one type of S orbital. P, there are 3 different types of P orbitals. D, there are 5 different types of D orbitals. And F, there are, not F, 7 different types of F orbitals. Each orbital could hold a maximum of 2 electrons, which means, again, if we sort of max out the electrons, it is 2 for S. It is 6 if we fill up all of the p orbitals on a particular energy level, which is sometimes referred to as a subshell or sublevel. We can do 10 if we fill up the D subshell or sublevel, and 14 electrons if we fill up the F subshell or sublevel. Again, there's 7 different orbitals. Each one can hold 2, and that would obviously be a maximum of 14 electrons. Sort of the basis of, where we see these orbitals and how many orbitals and sort of their orientation in 3-dimensional space is what is referred to as the quantum numbers. There are 4 different types of quantum numbers. There's n, which basically can have values of 1 through 7, and it is basically the energy level, with n equals 1 being the ground state, which is the lowest in energy, the closest to the nucleus, and anything above sort of that n equals 1 state is considered an excited state or an higher in energy, obviously further away from the nucleus. There's also a quantum number which is referred to as L, the angular quantum number, and that has values of 0 to n minus 1. And this will sort of tell you the type of orbital we're dealing with for the most part. So for example, if our n is equal to 1, our L possible value is basically 0, as 1 minus 1 is 0. So that would be the only value that you could have. A value of 0 for L tells you it is a s orbital. So s orbital is a 0 for the L value. P orbital is on the second energy level, which is a 1, a 2, and a 3, so forth for each of those. A 3 meaning the F orbitals are involved. As we go past F, as we talked about, I think it was a question last time, it does just go alphabetical after that point. So you just kind of go alphabetical, D, F, and then G, and so forth. We don't really get into any of those on electron configuration, but that's sort of how you would identify those guys. M sub L is the magnetic quantum number there. It goes from minus L to 0 to plus L, and these are all just whole numbers going from the negative value of L to the positive value of L. And it really tells you the orientation in 3-dimensional space of those orbitals. It will also tell you really, how many orbitals there are. So for example, if we had an L value of 1, the possible values of M sub L is minus 1, 0, and 1, which are basically the 3 p orbitals, the px, the py, and the pz orbital is what those guys would relate to. M sub s is the spin quantum number, and it basically has values of plus or minus a half. It's basically the spin on the electron in an orbital. And by notation, if we have an orbital there, if the arrow is heading upwards, that is what is considered plus 1/2. And if we have an electron represented by the arrow there that's sort of going downwards, that is represented by minus 1/2 in terms of the spin quantum number. Using really the quantum number is the basis of sort of electron configuration and why we say, hey, there's only like, say, an s orbital on the first energy level, and really, you know, what orbitals that we do see. So on that one, we have just a 1s orbital on the first energy level. When we get to n equals 2, we have also an s orbital, and that is again where the p's start. N equals 3. We have our s's, we have our p's, and we also have, if I squeeze it in there, our d's, and so forth as we go through the different orbitals. Remember that for every kind of individual L value that you have, you could have some M sub L values specific for that particular L value, and so forth. This led us into, at the very end there, talking about electron configuration, sort of the order. We also saw the different orbitals and so forth. And this is the order which electron configuration basically goes. Electrons go into the atom lowest energy first, and then kind of follow their way up to the next highest in energy and so forth. And what happens as we move past a hydrogen that has 1 electron is there is some energy shifting in the different orbitals that are there, and it does affect the order at which the electrons go in. It stays pretty much like you would expect. We could create this, and like we did last time, by just starting with first energy level is the 1s, second energy level is the 2p, the d's appear on the third, and the f's appear on the fourth, and you basically just fill in the numbers underneath it, obviously going down. So the order here does really work pretty well. You know, it goes, you know, 1s and then 2s, and you zigzag back here to 2p, 3s, and then the 3p. And here's really where the difference, you know, does occur for most of the electron configuration. The 4s, for example, or really the s orbitals, do actually end up being lower in energy than the 3d orbitals, for example, here. And that means that the electrons would go into the 4s first and then populate the 3d after that. And as you can see here, after the 3d, it then would go to the 4p after that and sort of finish that up. We will talk about here today as well. There's also a weird thing that sort of happens. You know, there is a switch that occurs in the energy of these orbitals. Once electrons start to go into the d orbitals, they're super close in energy. But upon filling, which is how we write electron configuration, the s's come first and then the d's afterwards. They actually do switch around, and the s's actually end up becoming higher in energy than the d's. And what that really affects is when something would lose electrons, you know, which electrons they would sort of lose first. Any questions on any of the stuff we talked about there last time? Okay, so let us go this way here. All right, so just kind of go through this again. For a principal quantum number of n is equal to 3, we want to determine the number of allowed subshells, the different L's. I think we kind of went through this one, but just one more time here to go run through it. If n is equal to 3, that means the possible values of L would go from basically 0 to 1, and then n minus 1 is 2 in this case. 3 minus 1 is 2. Those would be all the possible values here for L. Remember, this basically tells you the type of orbital you're dealing with. So we definitely have an L that's equal to 0, which should be an s orbital. More specifically, because it's on the third energy level, it would be a 3s orbital. That's what the 3 stands for, that it's on the third energy level. We have a 1, which would represent a p orbitals. And obviously here that would represent the 3p orbitals in this case. And we have 2, which is our d's. And that would represent our 3d orbitals. So again, for each of those L values, L is equal to 0. your M sub L would be 0 as well. Your M sub S could be plus or minus 1/2. For your L that's equal to 1, your M sub L could be -1, 0, and +1. Those would be the 3 different p orbitals that we see. And for each of those orbitals, they could either have an electron kind of going an upwards way or downwards way, which is plus or minus 1/2. And obviously our L is equal to 2 would have a M sub L that is -2, -1, 0, +1, +2. Again, if you sort of add all those numbers up, you have 5, which is the 5 different d orbitals that we see. And again, each of those guys could have an electron that's either +1/2 or -1/2. Any questions on any of that there? And obviously, I just did it there for our L is equal to 2. Again, it would run from -2 to -1 to +2. Again, these would be our 5d orbitals that make up our 5d subshell here. Not our 5d, but our 5d orbitals, our d subshell here in this case. Any questions on quantum numbers, how to assign them? Okay. So we talked about this last time. Again, these are our s orbitals. There's our p orbitals. Obviously, those are our d orbitals. And again, as we talked about, sort of probability, ideally where we would find electrons, high probability near that nucleus in the center in our Fs. So as I mentioned before, electron spins, quantum number is the M sub S, and it can have +1/2 or -1/2. There's an important rule that says it's the Pauli exclusion rule, that no 2 electrons in the same orbital can have the same set of 4 quantum numbers. So what that impacts, as we will see here in just a second, again, how the electrons sort of go into the individual orbital. But basically, to sort of get around that, they do need to have sort of opposite spins. So atoms with more than 1 electron, again, since the pathway of those electrons, as we talked about, is sort of unpredictable in that sense, we don't know exactly where they are, but again, we refer to those electrons being housed in these sort of probability maps, which again are our orbitals, our s, p, d, and f. And jumped the gun a little bit with showing the configuration there, but again, what that affects is there's some different penetration effects. The 2s orbital electron penetrates the nucleus more than a 2p. There is some differences in the energy level of these different orbitals. Again, you can think about, obviously, there's a lot of electrons near each other, which, they're going to want some space as we start piling in a lot of electrons into an atom. And again, that gives us some differences in those orbital energy levels, which obviously affects the order at which those electrons really do go into the atom. There we go. And that's what those guys are. Okay, so let's talk about electron configuration and do some examples here. So as I mentioned, sort of the last time there at the end, pretty much if you know the order here, or you're able to sort of recreate this like I'm doing right now, which is not too hard to do. And again, you can start with the 1s, the 2p, the 3p, 3d, and the 4f, and then really just fill in the numbers afterwards. Once again, we always start at the top and sort of follow the arrows, kind of zigzag back to the arrows. And again, this in combination with the idea that S could hold, again, a max of 2 electrons. If you filled up all the p subshells, we're looking at 6 electrons, d subshells, 10 electrons, and F subshells, 14 electrons. You pretty much will be able to write any electron configuration that you would need to do. And again, we always start here at the top here. So let us do some of these here and write electron configuration. So we will start with, why not start with hydrogen? So hydrogen is atomic number 1, which means it has 1 proton. Obviously, if it is neutral, it would have 1 electron as well. So once again, we start at the very top there, and the electron configuration would be 1s1 in this case. The first number here is the principal quantum number, the n. Tells us basically the energy level it's on. That is the orbital, our subshell that the electron is in. This is how many electrons are in there. We also could write and sort of display electron configuration using what is referred to as orbital diagram. And orbital diagram is basically either you can use boxes or you can use lines to represent the orbitals, and you could use arrows to represent the electrons that there are. So here I will just use a box here. So in this case for hydrogen, we have a 1s orbital, and our orbital diagram here would look like this with 1 arrow pointing in the upwards direction. Now, always when the first electron goes into the orbital, it does sort of by designation point upwards. We can assign our quantum numbers to this electron here, just to tie this into quantum numbers. If we went with this electron here, the n would equal 1, as it is obviously on the first energy level. L would equal 0, which it is a s orbital we're dealing with. Our m sub L here would be 0, and our m sub s would actually be plus 1/2 in this case. Plus 1/2, only plus, not plus or minus, but just plus, as it is pointing in the upwards direction, indicating sort of the positive spin that would occur here. Any question on any of those things there? Continuing on to, say, helium here, which is number 2 there on the periodic table. That means it's got 2 electrons. Again, starting up here, up on top and coming this way, we would again get an electron configuration of 1s2. And again, that is how you're supposed to write it. Big number, small letter, and superscript number up on top. This means that if we were to do our orbital diagram here for helium, we basically have a couple of options. We would put our first electron in, and then perhaps we could put our second electron in like that. We could do maybe our first electron up and our second electron down. Now, is there a difference the way we do this? There is. So, for example, we did the 4 quantum numbers for this particular guy here, which is what we see right here. Our n would equal 1, our L would equal 0, and our m sub L would be 0, and our m sub S would be plus. Now, if we did the quantum numbers for this electron here, the second one in there, it would also end up with the exact same 4 quantum numbers. And that would end up being a violation of Pauli's exclusion rule, which says no 2 electrons can have the same 4 quantum numbers. So We would actually not do it this way because that would violate Pauli's exclusion rule. So the way that we're able to get around it is actually doing it the second way here. And the reason for that is our first electron here would be this 4 quantum numbers. Now, if we did our second electron there, I'll just put a box. You don't usually box them individually, but I'll put a box here around this one. If we did the quantum numbers for this guy that's in red, n would equal 1. L would equal 0 as we're still a s orbital. M sub L would equal 0. But in this case, the electron is pointing down, which means it gains the negative 1/2 spin. And it is that little difference right there in the spin of those two electrons that make them have different quantum numbers or set of quantum numbers. And that does not violate Pauli's exclusion rule. So based on Pauli's exclusion rule, the first electron always goes upwards. The second electron needs to go in the opposite direction in terms of its spin. And when we have that situation where we have opposite spins on electrons, this is what is sometimes referred to as paired spin. They essentially, for most part, kind of cancel each other out in a sense in terms of their spin. One's plus a half, one's minus a half. So everything's all good in that case. So we would never, when you draw an orbital diagram, show both arrows in the same orbital heading in the same direction, either upwards. And you would get the same thing if you did them both going down. They both would end up with the same 4 quantum numbers. So it's always opposite spins when you put the arrows in the boxes or lines. And they should always go kind of, again, first one up, second one down to pair it off. Any questions on that there? Okay, so continuing on here with electron configuration, number 3 is lithium. Here is next. So once again, starting up at the top here, we would do 1s2. As we can see here, there is no more room in this box. That means we need to then zigzag back now to the 2s orbital and put that in there. So this would be 1s2. 2s1. In this case, if we count up the top numbers, that is 2 and 1 is 3 electrons. So that is 3 electrons that have gone into this atom. In this case, if we were doing some orbital diagram, we would need a box or a line for the 1s. We would also need a box for the 2s. And just the same room here, I'm just going to do them side by side. Technically speaking, if you did it based on energy, the 2s should be higher in terms of the location there. We would put our first electron into our 1s. Our second electron would go downward there. Again, having the opposite spin. Our next electron in the 2s would go in the upwards direction. At this point, we have our 3 electrons. We want to do our quantum numbers for this particular electron. What would the n value be? N would equal 2 as it's on the second energy level. L would equal, in this case, now n could equal 2. L could have values of 0 and 1 in this case. In this case, the value of L is 0 as we are still dealing with an s orbital in this case. Our m sub L here would be 0, and our m sub S would be plus 1/2. And those would be the 4 quantum numbers for that specific electron. You can see that you can obviously go each individual electron and specifically give the 4 quantum numbers for them. Any questions on that there? Now, in this case, we basically have 2 electrons on the first energy level, and we have 1 electron on a higher energy level, which would be the second energy level that is happening in this particular case. Continuing on would be beryllium, which is 4. And that would, again, starting at the top, 1s2 and now 2s2 in this case. Once again, if we did a little orbital diagram, we would have 2 electrons in there. Now for our 2s here, 1 electron up, 1 electron down. Can I put any more electrons in that s orbital? At this point, it is full, so we would have to obviously go to the next one. Since we're doing some quantum numbers here, why not? Let's throw the quantum numbers for this guy. And in this case would equal 2. Once again, this is on the second energy level. The L, once again, would be 0 since it's a s orbital. The m sub L would also be 0. And in this case, the ms would be minus 1/2 as it is pointing in the downward direction here. And again, it is that difference between the spin quantum number in each of those that allows it not to violate Pauli's exclusion rule. They do end up with a set of different p or quantum numbers. Any questions on that there? Going to boron here, which would be number 5, 1s2, 2s2. We have obviously used 4 electrons. Whoops, get back. That brought us to here. So obviously in this case, now we're going to need to go into the 2p subshell there to put our next electron. And that would then give us 2p1. Once again, counting the top numbers there, 2, 2, and 1 gives us 5 total electrons. In this case, we have how many electrons on the second energy level? There are 3, 2 in the S and 1 in the P. And obviously we still have our 2 electrons there on the first energy level, which would be in the 1s. In this case, we do some diagram here. We would have a 1s box. We would have a 2s box. And because that's a 2p subshell, we would have actually 3 boxes to represent the px, py, and pz orbital that there are. In this case, our first one would go into the first orbital and then opposite pair. Second one would go in and come down. Now, in this particular case, we would then put our very first electron there on the left orbital there, which is our px orbital, heading in the upwards direction. Now, if we do a little bit of quantum numbers there on, say, the last electron, since we did the previous one before that, my n value here would still be 2 as we're in the 2p orbital. My L value would actually be which one here in this case? L value should be only 1 in this case. Remember that the L value of 0 is an S, L value of 1 are p orbitals. Since we're specifically talking about the electron in the p orbital, it does need to be an L value of 1. It could not be 0. Our m sub L in this case actually would be minus 1 only. Because of this, our m sub L could go from minus 1 to 0 to plus 1. And that basically is how these orbitals are written. That is minus 1, 0, and plus 1 coming this way. Again, for our px, py, and pz orbital going across there. And our spin on this particular one is going to be plus 1/2 as it is heading in the upwards direction. Any questions on any of those there? That then brings us to carbon, which is number 6. So carbon is number 6. And obviously we can see we have lots of room here in this subshell to put electrons. So we would do 1s2, 2s2, in this case 2p2. Once again, we draw our orbital diagrams here, 1s, 2s, and once again, not drawn correct in terms of energy, but just to save space, we'll do it this way, 2p. And again, first one would go in upwards, second one would go in down. First one here would go up, second one would go down. First one here would go up. And now we have some options here in terms of where we could put our next electron. We could, if we wanted to, perhaps put it here. We could put it here. And I guess you could put it on the other side. So these are two options, and let's talk about which one is merely the right option here. And the right option is going to be this particular one. And this is what is referred to as Hund's rule. Hund's rule basically says that the most stable arrangement for electrons in an orbital is to maximize parallel spin. So earlier we talked about this idea here, which is paired spin. So that clearly is not maximizing parallel spin. Parallel spin is where everybody's heading in the same direction. And that is what we would see in this configuration here. So when you hit a subshell that has multiple orbitals in there, they basically all go in up first in the same spin, and then they come back and start pairing off with each other when there's no other options at that point. So the way we would want to do the orbital diagram is what is in the box there. This maximizes on the bottom here parallel spins, and that would mean that the next electron would actually go into the orbital to the right there, which in this case would be the PZ orbital to the right. At that point, once you fill up all three of those kind of heading in the same direction, then you would go back and pair off again if you had more electrons. Any questions on that there? All right, so that is carbon. Might as well finish out the first 10 here. We'll go to nitrogen, which is number 7 here. So nitrogen would be 1s2, 2s2, 2p3 at this point, giving us our up and down, our up and down, and our up, and now our up in this case, again, maximizing that parallel spin. Let's do some quantum numbers. We didn't do it on this guy, so we'll take a look here. This guy previously, which would still be this electron here, this would have, again, an N value that is 2. This would be a L value that is a p orbital, which would be 1. This would be an M sub L of 0. Again, this guy right here is -1, 0, +1 for the M sub L. And our spin again here would be +1/2. Coming down to this guy here, and once again would be 2. L would be 1 because it's a p orbital. Our M sub L tells us it's in the +1 orbital, which is what that guy is right there, +1. And our spin, again, also going +1/2 in that case. Any questions on that electron configuration, orbital diagram, how to assign the quantum numbers there? All right, so like I said, we'll finish out the first 10 here. So next would be oxygen, which is number 8 on the list here. So oxygen, which would be 1s2, 2s2, 2p4, if I add that right there. Once again, we would have our orbitals. We would go up, down, again, fill this guy up, and up. At this point, we would then go back to our first one and put our 4th electron heading in the opposite direction so they don't get the same quantum numbers, and they're paired off at this point, still maximizing as much parallel spin as we can by having those two by themselves over there. So we will do this electrons for quantum numbers. This again would be N is equal to 2, second energy level. L is equal to 1. It's a p orbital. In this case, the M sub L, we're now back to the first orbital, which would be -1. And the spin on this guy would be -1/2 as it is pointing in the downward direction. Next would be fluorine there, which should be 9. 1s2, 2s2, 2p5. We're getting close to filling that p subshell here. So our 1s would have electrons. Our 2s would also have an up and a down. And now again, our 2p here, up, 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 now pairing down and down. And if we look at this electron here, n would equal 2. L1 again is still a p orbital. We are now moved to the middle box there, which would have a representation of 0. And our electron heading in a downward direction there would be -1/2. Any questions on that one there? Lastly, then, would be neon in this case. So neon would be 1s2, 2s2, 2p6, which is the last spot that we have available for us there in our p subshell. Doing our diagram here, up, down, up and down. Again, these go in one at a time in the upwards direction, then coming back and pairing off. Oops, if you actually get it in the box there, pairing off. And our last electron here, having a n is equal to 2, L is equal to 1, M sub L is -1, and the S is -1/2 in this case. Any questions on electron configuration, how to draw orbital diagram, how to assign us quantum numbers? All right, why don't you try a couple here? Let's do why don't you write just the electron configuration here for let's do magnesium, which is 12. Let's do nickel, which is 28. And let's do strontium, which is 38. So you could write just the electron configuration. You also draw the orbital diagrams. And why don't we do the 4 quantum numbers for the 11th electron for magnesium. Let's do the 24th electron for nickel, Ni. And we'll do the 37th electron for strontium. All right, take a few minutes, see what you come up with. Okay, let's take a look, see how you're doing. So we'll start, we're just going to do electron configuration, which is the 1s2 and all that good stuff. So 12 for magnesium here would be 1s2, 2s2, 2p6. Again, if I count up the top numbers there, 2, 2, and 6 is 10 electrons. So I do need obviously 2 more. So that would then take us to 3s2 would be the electron configuration for magnesium. Any questions on that one there? All right, I'm going to lay all the configurations out first, and then we'll answer the second question there. So nickel, which is 28, again, starting at the top, would be 1s2, 2s2, 2p6, 3s2. Once again, if you count the top, that is 12. I need to keep going. I then could go to 3p6. That's now going to give me the 18, which is closer. Remember that after 3p6, it then goes 4s2 would be the next one that it would go. And that is, again, because the 4s is less or lower in energy than the next ones that we need, which is actually the 3d should come next. In that case, we would need 3d8 8 in this case. So again, if we count at the top, that's 2, 4, 10 with the 6 and 10, so that's 28. And again, that would obviously be nickel's configuration. This would be magnesium's. Any questions on that one there? So coming here to strontium, I'll just start it kind of underneath it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. In this case, we're going to use all of those d orbitals, and that's going to give us 3d10. At this point, we then would do a 4p6 next, followed by a 5s2 in this case. And that obviously should be strontium's configuration. Count up the numbers, should have 38 there, I hope, in this particular case. First off, any questions on writing the electron configuration? Now, I did ask, what are the 4 quantum numbers specifically for each of these electrons here and each of those guys? So, if it helps you visualize, you can do the orbital diagram, but you don't have to necessarily do the entire orbital diagram. You could just do the one for the particular subshell that it may be in, or orbital it may be in. In this case, my 11th electron is found right there in the 3s orbital, right? Because that's up to 12. And that means that that's a 3s orbital, which basically would look like this. And it would be really the first electron that goes in there, right? Because the second one gets us to 12. So the first one that goes in there would get us to 11. And that would be our 11th electron. And because it's in the 3s orbital, the n value here should be 3. And once again, because the n value is 3, L could be 0, 1, or 2. In this case, the L value is which one? It is actually only 0 because we are in a s orbital. It cannot be 1 or 2 because we're not in a p or d orbital in this case. So just because it's possible, and it is possible because on the 3rd energy level, we have those orbitals available to us. But since we're talking about this specific electron, we're talking about where it's housed. That means specifically here, our m sub L would be 0. And since it is the first one into that orbital, it should have a +1/2 in this case. So again, you don't necessarily have to draw an all out, kind of isolate the orbital. If you're asking really specifically, just about one particular electron, it's easier to do. You could draw it all out as well. Any questions on that there? Let's do the same thing with this one, which is 24. So 24 electrons would put us in here is where we would find our 24th electron in that subshell, which is our D. And again, in this case, you could just draw out the Ds, which would be 5 boxes because there's 5 different orbitals. And in this case, up to that point, we have 20 electrons, right, up to the box, which means my 21st electron would go up, my 22nd electron would go up, my 23rd electron would go up, and my 24th electron would go up at that point. Again, that would be 10 and 10. 2, 3, 4. So really, this is the electron we're looking at. By the way, if we finish it out there, obviously, we have 1, 2, 3, 4, 24, 25, 26, 27, and 28. But again, it would be this electron here that we're actually dealing with. And that should be number 24. And that means that the n value here would be 3. In this case, the L value would actually be 2 in this case, as we are dealing with the d orbital here. Our m sub L could have values, again, of minus L to plus L. And again, it really does just kind of go in order. If you draw the boxes like this would be -2, -1, 0, +1, and +2. So we can see the electron is in the +1 box in this case. And it is also pointing in the uppers direction, which should be +1/2. Any questions on that there? Lastly here, if we're going to kind of do the same thing for our 37th electron that went into this guy for our last one, it should end up in this orbital here, which is a s orbital. That means we would have our 5s orbital. First electron would go in, second electron would go down. In this case, it is actually the first electron that we're looking for, which would be technically the 37th electron. And in this case, n would equal 5 because of that. And again, our L value, because n equals 5, could be 0, 1, 2, 3, or 4 if n is equal to 5. And that means in this case, it is in an s orbital, which means the L value does need to be 0 here because 0 represents the s orbital. That means the m sub L would also be 0. And our spin would be, in this case, plus 1/2 as it is going upwards. Any questions on any part of that there? Where any numbers came from or how we figured out any of those things? So again, you don't necessarily have to draw the orbital diagram for anything if it didn't ask you to do so, but sometimes it can be helpful to visualize sort of the quantum numbers if you need to do it for a specific electron. So you could kind of just isolate the orbital or subshell that you're dealing with and put the arrows in to help you understand sort of where it ended up and which direction that is going. Any questions on any of that there? Now, while we have some of this up here, let's also talk about another way that is very common that we sort of write electron configuration. And that's sort of a shorthand, if you will. So let me just rewrite the electron configurations here on the next page so it's not so crowded. So we had magnesium, that was 1s2, 2s2, 2p6, 3s2. We had nickel. That was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8, and we have strontium. That was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and 5s2. So clearly this is electron configuration completely written out. But if we look at this configuration, for example, up to this point here, that is how many electrons? And the yellow box is 2, 4, 6 is 10 electrons. When we look at the periodic table, number 10 is neon, right? So we can write sort of a shorthand for this where we put in brackets neon to represent its electron configuration, and we could continue on with 3s2. This is sometimes referred to as noble gas configuration. Because what goes in there is a noble gas, which is the last group there on the periodic table, group number 8, where neon is over there. If we could also do the same thing here up to, go up to here, actually. Up to here, if we count up the electrons here, that is 2, 4, 10, 12, 18. And 18 on the periodic table is our friend argon, which is also a noble gas in group number 8. And we could continue on with the configuration of 4s2, 3d8. And we could also do it for the really long one down there, which we would actually go up to here. So all the way up to there should be 36 electrons. And 36 electrons, if we look on the periodic table, is krypton, I think, there. So we put krypton and continue on with the configuration of 5s2. This was sometimes again referred to as noble gas configuration. It is a noble gas, which is group 8 on the periodic table, the last group all the way to the right there. That is what needs to go in the brackets. So it's always the noble gas that comes right before whatever you're writing electron configuration for. You put in brackets, and then you just kind of continue on with the electron configuration. Any questions on that there? Any questions on writing electron configuration fully out, shorthand, if you will, orbital diagrams, quantum numbers? Hopefully you can see how they all sort of tie together and relate to each other. All right, let us also, since we're talking about electron configuration, let us talk about some other electron configurations and some that are maybe a little bit different than we might anticipate. There are some exceptions. So let's get to those. Where do those go here? Let's see here. All right, that's basically what we talked about here. Hund's rule, we talked about the orbital diagram. We talked about here. Where are we at there? Actually, you know what? I'll go back and do it back there. Hang on a sec here. Let's actually do it here, I think. All right, so let's talk about a couple of things. There are a couple of exceptions, and we'll see a slide a little later. We'll look at some of those in just a sec. Where there are some differences in how electron configuration is actually written. Two really notable exceptions that most people learn about is chromium, which is 24, and copper, which is 29. And in terms of chromium, if you were just to follow sort of the zigzag guide there, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. The exception actually happens right here, and that is with the s and the p orbital. It's been found experimentally to actually contain and be more stable with one more electron up in the d orbital, one less electron in the s orbital. And that does give us a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So that is one major exception, extra electron up in the d orbital rather than the s. That happens again because they are super close to each other, as we talked about previously in terms of energy. And again, we get that sort of switch in energy that actually occurs. So it doesn't take a lot for that electron to kind of go up into the d orbital. It also, if you think about it in terms of the d orbital, really does maximize parallel spin, which is our Hund's rule, by kind of doing that as well. Copper is a very similar exception. It is 1s2, 2s2, 2p6, 3s2, 3p6. Once again, it has one less electron in the s, one more electron there in the d. So it looks like 3d10 in this case is the exception. And what that does is basically pair up all of the d orbitals and leaves our really higher energy electron there being unpaired in the 4s that ends up happening. Actually, when you look on the periodic table below chromium and below copper, there's a lot of very similar sort of exceptions that occur there. And let me go find that slide here. Where's that slide? There we go. There we go. Here, now here's some other exceptions, which is also on your notes here. So again, below chromium and copper, there's a lot of other exceptions. And again, you can see something like MO has a similar one, extra electron up there. Something like PD actually will promote both electrons up there, and it has none in the S. Things like silver also has an exception to the normal electron configuration. So if you kind of go chromium and copper on the periodic table, go down and kind of over towards the center, there's a lot of very similar exceptions that we come across here. For us in this class, you will be responsible just chromium and copper, even though those guys underneath there have some other exceptions and stuff like that. You could write them like you would with the zigzag thing, but for sure you should know the exceptions for those two. And you should be aware, again, underneath there, there's a lot of sort of exceptions that occur in the transition metal region. Any questions on that there? So some of these guys we flew by here. So transition metals, as we talked about, they're worth writing electron configuration. It's really where the D subshells occur. Transition metals start over there at number 21, and is in the middle there. 21 to zinc, and then down is the transition metals, is where our D orbitals are. And they basically have incompletely filled or filled D subshells as you go down through them. We did some of these electron configurations, so that's okay. Now, you can sort of count off electron configuration from the periodic table if you want. You do need to know a couple of things that are a little bit different. For example, our period numbers here, which is our 1, 2, 3, 4, 5, 6, 7, those are really our N numbers. So those are like our N numbers. And you basically can just sort of count it off. The first two groups is the S block. Group 3 through 8 is the P block over here. The transition metals, which are these middle guys, it's the D block. And the two guys on the bottom there is what is referred to as the F block. So for example, we did magnesium there, which is right there. And if we were going to sort of just count it off on the periodic table, we would start up here and we would go all the way over here, and that would be 1s2, coming back here, 2s2, 2p6 all the way to the end, and then 3s1 and 3s2 would be our electron configuration by counting it off like that. If we were to do something like the second guy that we did there, which was nickel, I think, and nickel is there, so nickel should be right about there, should be nickel. And we could count it off the same way. We would start at the top here. This would be 1s2 to there, 2s2, 2p6, 3s2 coming this way would be 3p6 to the end, 4s2. Now the important part here is the d orbitals is where our transition metals start, and this guy right here is actually 3d, not 4d, even though it's on the fourth energy level there, our fourth period. So the 3ds are one behind the period number. That's 3d. This would be 4d, 5d, and 6d happening there. And really the f's are two behind the 4F and 5F, the period number as those two should go right there. So they're two behind. So as we would be counting, we want to make sure we didn't screw up, and it would be at this point, again, 4S2, and this would be 3D, 1, 2, 3, 4, 5, 6, 7, and 8. 3D8 by counting it off right there. So you can use the periodic table to sort of count off electron configuration if you know what you're doing. Again, the d orbitals 1 behind, the f orbitals are again 2 behind the period number. I personally would more likely use the zigzag guy that we made there and we talked about at the beginning. You for sure probably won't screw up if you use this guy. And once again, it's not too hard to sort of create it. You can pretty much create it pretty quickly. And again, if you go this way, you know, you'll pretty much be in good shape. If you count off the periodic table, again, there's a little places where if you're not really careful, you might get the wrong sort of counting of the electron configuration. Any questions on how to use the periodic table to count electron configuration? All right, then let's talk about a couple other things with electron configuration here. We'll go back, find some pages. Clear. So we talked about things here that obviously do not have charges, but what happens with electron configuration once we do have things that have charges? So for example, we did magnesium there. And again, that was 1s2, 2s2, 2p6, 3s2. If magnesium had a +2 charge, it would then have how many electrons? So instead of 12, it had +2, means it lost 2 electrons. So it would actually end up with 10 electrons, this guy, which means this configuration would be 1s2, 2s2, 2p6 would be the proper electron configuration for magnesium with a +2 charge. If we had something like oxygen with no charge, as we did earlier today, that would be 8, which would be 1s2, 2s2, 2p4. Oxygen that gains a -2 charge would then end up with 10 electrons as well. 8 + 2 would get us to 10. It would also end up with an electron configuration of 1s2, 2s2, 2p6. 1s2, 2s2, 2p6 is 10 electrons. Who on the periodic table is 10? It is neon that is 10. So this is the same electron configuration as basically neon. So neon, magnesium with a +2 charge, oxygen with a -2 charge, they all have the same electron configuration. And things with the same electron configuration, they are said to be isoelectronic with each other. So things that have the same electron configuration are referred to as being isoelectronic, as we will talk about in the next chapter as well. Oxygen, by gaining 2 electrons, ends up at neon, which is the noble gas that comes after it. Magnesium, by losing 2 electrons, becomes neon by going backwards to the noble gas there. That is basically the basis of all bonding. The basis of all bonding is for everybody to end up with the same electron configuration as a noble gas. And the way metals and nonmetals do that when they come together is metals will lose electrons and back up to the noble gas that comes before them. Nonmetals will typically gain electrons and go forward to the noble gas that comes after them. And that allows them both to really achieve noble gas configuration. In the case of nonmetals and nonmetals, they do that by sharing electrons. It allows everybody to get to 8 electrons, which again is basically the same sort of electron configuration as a noble gas. So the basis of every bonding aspect is everybody's really trying to become like those noble gases. and end up with the same electron configuration. The reason for that, as we'll talk about, is noble gases are extremely stable and basically chemically inert. So that's sort of what everybody's trying to achieve in a bonding situation. Any questions on things with charges? Now, there is sort of an exception in terms of people sort of going back to the noble gas configuration, and that's with transition metals. And transition metals, again, are right there between group number 2 and group number 3 on the periodic table. Again, 21 to 30 and down is the transition metals. Transition metals, when they lose electrons, are a little bit different in terms of what happens. When people lose electrons, they typically will lose the highest energy electrons first. And those are what are referred to as valence electrons. So valence electrons are the highest energy level electrons. So for example, that's what we see here with magnesium. That is the 2 valence electrons that we have in magnesium, the highest energy level. So when it loses those 2 electrons, it is those that get lost first. That leaves us these electrons here. Again, these are what are referred to as valence electrons. The lower energy levels are what are referred to as core electrons, and it is those valence electrons that are lost here. When we look at oxygen, it is actually here where it gains the electrons, by the way. But when somebody loses electrons, they always will lose those highest energy level ones first, which are the valence electrons. So what happens with transition metals, if we look at, for example, something like iron, which is number 26 on the periodic table there, and we write the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, if I can get that there, 4s2 next, and 3d6. Now this again is, as we talked about, the filling order at which the 4s orbital is lower in energy than the 3d. So the electrons come into here. But what happens as we start to populate the d orbitals, there is again that sort of switch in energy that occurs. And this really occurs with transition metals. And what ends up happening is the 4s electrons actually end up being higher in energy than the 3d. So basically what that means is when transition metals go to lose electrons, they will always lose the s electrons first. And then if necessarily, they will delve into the d orbitals, which are the next lowest in energy or highest in energy. So what would happen in the case of iron with a +2 charge is that you would end up with 24 electrons necessary. So what will happen is it will actually be these 2 electrons here that actually get lost first. And that would leave us a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, or it will leave us argon 3d6 as the electron configuration, where these 2 electrons are lost first. So in terms of the filling process, they're lower in energy, they get the electrons first, but what happens is there is that switch in energy that occurs. And what's important about that is once those transition metals start to lose electrons, it is those s electrons that are always lost first. That means if iron had a +3 charge, it would end up with 23 electrons in this case. And the configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. At this point, it will once again lose these 2 electrons, but it still needs to lose 1 more electron and the next electron would come out of here, and it would lose this electron here, and we would actually end up with 3d5 in this case, and that would be argon 3d5. Any questions on that there? So the transition metals are a little bit different. They really do not get back to the noble gas configuration when they lose electrons. Only what is sometimes referred to as representative elements like sodium, magnesium, those guys, or aluminum. When they lose electrons, they go backwards to the noble gas configuration. Transition metals really typically will not get themselves back to that situation. Any questions on that there? All right, so why don't you try some here? Why don't we do, let's do calcium with a +2 charge, which is number 20 on the periodic table. Let us do nickel with a +4 charge. And let us do sulfur with a -2 charge. Okay, let's take a look since we're getting to the end here. So calcium with no charge is 20 on the periodic table. Again, with a +2 charge means that it has lost 2 electrons, which means it should end up with 18 electrons, which would be 1s2, 2s2, 2p6, 3s2, 3p6, that would be 18 right there. And that would also be argon's configuration there. Not 61, so just put a box around it. Any question on that one there? Nickel is 28 on the periodic table. It has a +4 charge, which means it has lost 4 electrons. That will take it to 24 electrons. Now, nickel with no charge would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. In this case, it will lose its 4 electrons. It will first lose, again, the s electrons here, since this is a transition metal. That is 2 electrons. It then would need to come into our d orbitals and take out 2 more electrons. And that would basically get us down to a nickel configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, or argon 3d6 would be the electron configuration for nickel. And again, because nickel is transition metal in that middle region, that will always happen. Once again, they will always lose those s electrons first. Lastly here, sulfur, which is number 16 on the periodic table. So sulfur with a -2 charge means that it actually gained 2 electrons, and it would actually end up with 18 electrons, which would frankly put us back to the same configuration right here. It would be 1s2, 2s2, 2p6, 3s2, 3p6 are once again argon's configuration. Any questions on how to write electron configuration with things with charges? So once again, it's only the transition metals, that middle region, that's a little bit different. Always the s electrons lost first. Then if necessary, you go to the Ds. In terms of group 1, sodium, and group 2 there, where magnesium is, and aluminum, if they lose electrons, will always be their last ones in the configuration, is the ones that are lost. Any questions on any of the stuff we talked about here today? All right, we will lay it up there for today.